is made of, I'd like to know at what angle and how big was the load that was applied. That's the question. Okay, so now, let me see, hold it a second. Okay, let me see if this is visible. Yes, okay, everything is visible. So we shall begin by focusing on the following. If we first look this is the neutral axis, and that's where the strain gauges are. If we look at the differential element at the neutral axis where the strain gauges are, we have to say, what are the stresses on that element? I don't mean numbers, but what nature do they have? There is certainly going to be a stress sigma in tension, right? Due to the P times the sine of theta that is pulling. And there is going to be, in addition, a shear stress, tau, right? Because of the P in this direction. Now, to know the direction of that shear stress, I can do this just to make sure that it's not really that critical, but I want to do it in the right direction. So you can see that if the component of the load is downward, the shear on a free body diagram like this would be upwards. So in this element, the shear is downward like that, because this is the phase that connects there. So I have a shear downward here, shear stress, a shear stress like that, and since those are rotating clockwise, this shear would be counterclockwise, and so that is that stress element. Now, is there stress in the y direction? Well, from a point of view of elasticity, they may actually be a little bit, but we will say that this stress is zero, because we have no way, we don't think there's any stress there. We're saying this is plain stress. It's like that. So this is our element as it begins. Okay? Now, if I look, this is my stress element at the location where I have these things. If we now look at the strain in the same position, I'm using this square to orient ourselves. I will say we know that there will be strains in the x direction. Okay? There will be shear strains. In fact, I don't know if I need to. Maybe I won't draw directions, not to confuse you with directions. Let me just say that. Okay. Oh, I'm going to go like this. Instead of doing this one geometrically, let me just say that due to this, there will be a strain in the x direction because of the sigma, right? And that strain in the x direction is one of the ones that we measured, and it's actually EA, right? Wow, these things are really giving me a hard time. Try again. Okay, the strain in the x direction here is E sub A, is the one that was measured. Now, it's probably the trickier part of this problem, which is to recognize that even though there is no stress in the y direction, there will be a strain because of Poisson's ratio. That is, when we take this thing and we pull it, it tries to come in on itself. So if we go to the stress-strain relationships and we say sigma in plane stress, so go to the plane stress equation that I put at the beginning of the class today and I have done in the past, and set sigma y equal to 0. If you set sigma y equal to 0, what you will find is this, that E divided by 1 minus nu squared multiplied times nu multiplied times epsilon x plus E multiplied times 1 minus nu squared multiplied times epsilon y would have to be 0. Because those are the stresses. I mean, that's the relationship that gives sigma y. Since that's the relationship that gives sigma y, let's see, this is the one that I was using. Since that's the relationship that gives sigma y, this I guess is the one that was working better, yeah. Then this cancels, and so we find that nu times epsilon x plus epsilon y must be 0. Therefore, epsilon y is equal to minus nu times epsilon x. So I repeat, this is the logic that we're using at this point. We're measuring strains like this and like this, but because of the load, we know we have a stress in x, and there's going to be shears due to this. Now you might say, what about the bending? Well, the bending would have contributed to sigma, right? But it doesn't contribute at all because it's at the neutral axis. So the only sigma that we get is from the tension part of this load P. And we get this shear stress due to this shear component of the load P. There is nothing in y. Now we switch hats and we look at strains. And we say, in the x direction, are there strains? Yes, this thing gets longer. In the y direction, are there strains? Well, yes, because if there are no stresses and we go to the plane strains formula, to the plane stress formula, with no stresses it requires that epsilon y be Poisson's ratio negative times epsilon x. That is, when this gets longer, this gets shorter. Okay, now that I know that, then we say, okay, fine. I now know epsilon A. So what I know is that epsilon, that is the strain in the x direction, is epsilon A, right? It's given in the book. And the strain in the y direction is equal to minus nu times epsilon A. So I know the two strains, right? Now I don't know the shear strain, but I do know the equation. Let me erase everything now. I do know the equation for rotating the stresses. And so I can say that the rotated stress at 60 degrees, which I am measuring, has to be the formula. And so the formula was Ex, which is Ea, plus Ey, which is minus nu Ea, divided by 2, plus epsilon x minus epsilon y, that is Ea plus nu Ea divided by 2 times the cosine of 2 theta, which in this case would be 120, plus the shear strain gamma xy divided by 2 times the sine of 2 theta, so this is the sine of 120. Okay? Now, what's the deal here? The deal is that we are measuring this strain at 60 degrees, right? We had one strain like this and one strain like that. So this is known, 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 this is not known, it's the only unknown, right? Therefore, I can find out what is the shear strain in the xy element because I was able to measure the strain in another direction. Okay, now if we do that, we actually, let me see if I solved for it. Yeah. So let's say that from this formula, we plug numbers and get gamma xy. Okay? Now we know that for the element that is in the neutral axis, like this. We know it's strain in X, we know it's strain in Y, and we know it's gamma XY. Because this EX is EA, which was measured, this EY is minus nu EA, and this gamma XY is whatever we got from here. Okay. Notice that how we did this had still nothing to do with the load. Okay? It only had to do with the fact that we said we've got an element under no vertical stress. And we have measurement in one direction and in another direction. More generally, think about it this way. There is no way to measure directly shear strain. So if I really wanted to know what is the shear strain, I would actually measure the strain in a direction and another inclined direction so that I can use this formula to find the shear strain, because I don't know how to measure it directly. Okay? So here we have now our shear strain gamma XY. Now the process is like this. Once we know gamma XY, once we have gamma XY is a number, right? But we plug it in. If you look at the stress-strain relationships, you can see that tau XY is just G times gamma XY. We know G and we know gamma XY. Therefore, we know tau XY at that location. That is, we know the shear. Now, the section is like this. Is B by H. Neutral axis in the middle, and that's where the strain gauge is, in the middle, right? So the question then is, what is the shear stress here as a function of the parameters of this problem? So you remember that shear stress is equal to shear flow divided by the thickness. In this case, the thickness is B. And the shear flow is VQ over I, and then we bring that B, so that's the shear stress. And we can equate that to tau XY, which we happen to know what it is, right? Now, let's fill in the blank. For this problem, what is the shear at the cross section? Well, the beam was like this, right? And the load was like this, and this was alpha, and that's P. So it's clear that V is equal to P times the cosine of alpha, right? That's the shear anywhere from the shear diagram. So we've taken care of this. Now what is Q? Well, we want this point here, so we want the shear flow here, right? Therefore Q is B times H over 2 multiplied times H over 4, or B H squared over 8. What is I? Oh, that's easy, right? 1/12 of BH cubed. So, if we substitute all those things in here, we would get that tau XY is equal to P times the cosine of alpha. You can check yourself, but it'll prove to be times 1.5 divided by BH. Okay? Now this equation, remember tau XY, you already knew it from before because you got it from here. So that's a number. You still cannot solve this equation because it has two unknowns, the load P and the angle alpha. So the other equation that you need pertains to what happens in the beam due to the normal load, right? I mean, to the other component of the P. The other component of the P is this way. And that is equal to P times the sine of alpha, right? And that gives normal stress. And the normal stress that that gives is equal to P times the sine of alpha divided by the area. Okay? And the strain that that stress gives, which is a sigma x, you can go to the stress-strain curve, the stress-strain relationship in plane strain with epsilon y equal to 0, and you will find that for this case is where the trivial relationship works, or the simple thing of dividing by E. So this is just this. But this, epsilon x, is the measured strain, epsilon A, that is given in the book. So we also know then that P times the sine of theta divided by B divided by H divided by E is epsilon A. And at this point the problem is done. Because then you can say, for example, dividing this by that, you would get P times the sine of alpha divided by BHE is equal to EA. Divided by this, which is P cosine of alpha times 1.5 divided by B by H is equal to tau xy. You can see that in this case the P's cancel, the BH cancels, okay? P cancels, BH cancels, sine of alpha over cosine of alpha is tangent of alpha, right? And so the tangent of alpha is equal to 1.5 times EA, what else? Times E, no. Yes. Divided by the gap, I think I made an error here. No, that's correct. Divided by the tau xy, yeah. It's okay, I just solved it differently. I was doing it before. I mean, this part is trivial now. Once you get the two equations, it's all very simple, right? Once you have the two equations, you got it. So you now plug in here, you solve for this, you get alpha. And once you have alpha, you can come here, substitute and find P. All right? So that is problem 719. The other problems on that homework are much, much easier. They're pretty much direct substitutions on the stress-strain relationships that we presented before. So you can give it a shot, and I hope that this will, I am sure that on a first inspection this problem will appear quite difficult because it puts many things together. There is a merit to that, which is take the time to think about it more than once, because like everything, the first time is difficult, the second time is a little less, the third time is a little less, and eventually, if you think about it a few times, it'll start appearing more or less apparent, okay? We have two strain gauges, one that measures horizontally, one at an angle. We use the one at an angle to give us the shear strain. Once we have the shear strain, we can get the shear stress. Once we have the shear stress, we got an equation that connects it to the load in this direction. We also measured horizontally. That allows us to connect it to the horizontal component of the P. We get two equations, combine them, solve the problem. I substituted the numbers and checked, and the book is correct. The answer in the back coincides with what we get. Okay, so I'll see you guys on Monday.